Hey, welcome back. Now we're looking at surfaces in space. The easiest surface we'll deal with are the cylinders. Okay, so we have cylindrical surface, and it's not what you generally think of like a Pepsi can as a cylinder. This means it's generated by some sort of curve in one of the planes, and then you're letting one of the other variables vary. So let's see, in the beginning, kind of on my own, sure, that's quartic surfaces, we'll get there. Cylindrical surfaces. Okay, so they give you an example here in figure 11.56, and it's drawing of x squared plus y squared equals sum a squared. So in the xy plane, it's a circle, right, with radius a. So here in the plane, once we get to 3 dimensions, though, we're letting basically z equal any real number we want. So in the xy plane, you'll see basically the trace of the circle, right? But then z can vary over the real numbers. So the resulting figure is kind of, you take this circle and just move it in the z direction, move it straight up in the z direction. So you'll end up with basically what will look like a cylinder. Okay, so if I connect this thing around and back here as well. So doing my best to draw this thing in 3 dimensions. Okay. Okay, so, and I mean, that's the same in any direction you want to go. So if you have x squared plus z squared equals a squared, your trace is in the xz plane then, and you would have your circle there. So let's draw the x, y, z axes here. You have x, y, and z. So this time the circle is in the xz plane, so kind of like this. And then to get the picture, you just move that circle in the y direction like this, and you would have your resulting figure like this. Okay. And in both, it goes in both directions. So z is allowed to vary over the real numbers, so it also is kind of funneling out in the other direction as well, if you wish. I don't know. And then you could, I mean, but for a cylinder, it's basically you could draw any figure you want in one of the planes and then just move it in the other direction, the axis which isn't specified, and you get pretty much any figure you want. So you see that kind of in an example 1. So these are cylinders too. It doesn't have to look like a Pepsi can to be a cylinder, right? So part A, z equals y squared. So what you do is just kind of draw it in the plane there, in the zy plane. So always put z on like it's the y on the vertical axis. So you have this figure, and then once you go to the xyz space, all you're doing is dragging that figure through the kind of in the x direction, right? So x, y, z. Here I'll put it in, I guess, red or something. Here it is in the xz plane, and then to get the full picture, you're just dragging it in this direction. Okay. And you get this kind of object. Kind of like a big ramp. Okay, so you see that in figure 11.58. And of course, then you could do it with that other guy, sine of x, and they've restricted its domain. So part B, z equals sine x. So this time the trace is in the xz plane. We're going from 0 to 2 pi, and it's sine. So it'll look like dish in that plane. And then to get the 3-dimensional surface, you're just going to pull it in the y direction. So this is x, this is z, of course this is y. So it's dish, and then if we pull it, it's going to go like this. It's an art form all to itself, right? And again, it kind of looks like a ramp type figure. Okay, and you see that done in the picture 11.58 again. Okay, so those are the easy ones to draw. We're not going to spend a lot of time on that. The quadric cylinders, the quadrics are, I think I was calling them the quartics earlier. They're quadric. I just messed that up. But these are kind of like your conic sections that you learned in Calc 2. You'll be able to identify them from the traces. So for example, this thing is called an ellipsoid. You see on the right of my screen here. And all of its traces are ellipses. So what you'll do is kind of a trace-by-trace analysis. You'll see what it is in the xy plane, see what it is in the yz plane, see what it is in the other plane, and then you kind of piece it together, and it's forced to have a certain shape. Okay. To help you along the way, you can use CalcPlot 3D. So CalcPlot, just go Google CalcPlot 3D. A community college, I forget where, some community college made this program. It's free, so you could go there. I relabeled my axes right off the bat. I just hit that button and relabeled my axes, and then you can get. Usually, I go to an implicit surface, and that's what I want to plot. And then you just plot it here in your in here. So the first, let's go ahead and just plot it using this computer software and see what happens. So example 2, we have, oh, really? Well, that's nice of them. So we have 4x squared minus 3y squared plus 12z squared. Plus 12 is 0. Okay. Let's see what it looks like here. And all we have to do is go 4x caret squared minus 3y caret squared plus 12z caret squared plus 12 equals 0, and then push that button and it should plot it. So it looks like we have a hyperboloid, 2-sheet hyperboloid. Sometimes you can't tell because the graphics are pretty bad. Anyways, the way you kind of identify this is you look head on, like at the xz plane. That would be equivalent to letting y equal 0. So if you let y equal 0, you're effectively in the xz plane, and you have the equation 4x squared plus 12z squared plus 12 equals 0. That's going to be 4x squared plus 12z squared equals negative 12, which isn't anything, right? That's 0. And if you look, yeah, so this is a 2-sheet hyperboloid. If you look in the middle, there's nothing in there. Okay, that would be the sort of center. But if you pushed out and you started looking at planes like y equals 3 or y equals 5, so let's try y equals 5. In that case, you would get 4x squared minus 3 times 25 is 75. Plus 12z squared plus 12 equals 0. So you get 4x squared plus 12z squared. 75 minus 12 is 63. That's definitely the equation of an ellipse, and that's what you're seeing when you look head on. As you go out in between here, certainly when y is 0, you have nothing, and that's this equation right here. There's no x and z that I can square and add together to give me a negative number, so there's nothing right there. But if you pushed out letting y equal some bigger number, then you see you get kind of an ellipse. If you look head on there, it's an ellipse. So from this trace, I would identify an ellipse, but in the middle, there's nothing. And that helps because there's two kinds of these, what they call hyperboloids of two sheets. And there's a hyperboloid of two sheet and a hyperboloid of one sheet. The one sheet has something in between, in the middle there. So let's see if they have pictures of all of the other one. There's the Pringle. Oh, they don't give you a picture of all of them. Isn't that nasty of them? Maybe you have to click on it or something. Oh, here we go. Plus. Okay, yeah. So there's this hyperbola at two sheets that has nothing in between. That's what's happening when you get that negative on the side. And then there's hyperbola at one sheet, and that will have an ellipse. So you can see the traces for those two objects are exactly kind of the same. The trace is ellipse, hyperboloid, hyperboloid. Let's get the other traces. So letting one variable equal 0 and seeing what happens in the other plane. So let's let z equal 0 and see what happens in the xy plane. Okay. So in the xy plane, you're going to get 4x squared minus 3y squared plus 12 equals 0. You could rewrite that as 3y squared minus 4x squared equals 12. And that's the hyperbola. Okay, so you're going to get some sort of hyperbola. Here's x, here's y, and it'll be on the y-axis. This guy will be an ellipse, something, And then let's see what the trace is in the third plane. The please, there you go, thank you. The YZ plane. So if you let x be 0, you get negative 3y squared plus 12z squared plus 12 is 0. And so you get 3y squared minus 12z squared equals 12. And again, that's a hyperbola, this time with the branches on the y-axis. Okay. So if you look at the picture head on, you get that ellipse. That's the xz plane. You can see xz on here on the right on the picture. If you look at the yz plane, so you can see y and z, you'll have hyperbola on the y branch. Okay, that's this this picture here. And then if you look in the xz plane, you will get you look at that xy plane, so like this, you'll get the hyperbola as well. So you can see this picture and this picture. Okay. So it's, I believe, from this analysis of the traces in the different planes that you're able to kind of piece together the form of the object. Okay, so each one of these pictures, if you know the traces, you should be able to kind of identify the form. So let's go through. Before I start, let me just note the possible traces. So I don't think I introduced this section. So the first section is cylindrical surface. The second section are the quadric surfaces. And we have possible traces. So these are the resulting objects you can get when you let z, x, or y equal 0. Okay. And it's basically just the intersection of the surface with a particular plane. Okay. So the first one is the ellipse, and hopefully we remember how to kind of draw. You don't have to draw these perfectly, but hopefully you remember that they all have the same kind of form: x squared over a squared plus y squared over b squared equals 1. I usually won't even bother putting it in that form. As you can see up here, as long as you know it's something squared plus something squared equals something positive, you have an ellipse. Okay. Then secondly, you have some parabolas. So usually you'll get something like y equals x squared, or even the other way around, so you have the sideways parabolas. Thirdly, you have the hyperbolas. So you know, that in that case, he'll have a subtraction sign between the squared terms. B squared is 1. So the branches will be on the positive terms. So if this is x and y, you'll have that format. Maybe I should put below it the other kind of form. So if you have x equals y squared, and you're plotting the xy plane, that will be a sideways parabola. If you have the y squared portion positive, and you're going in the xy plane, this will be a squared, b squared. The branches will be on the vertical axis, and of course for the ellipse, if the bigger number is with the y squared, then you'll have kind of the vertically oriented type ellipse. So if you have y squared over a squared, it's x squared over b squared. But you know, it's basically just get a nice little sketch, and so long as you can identify the resulting quadric, you're going to be okay. Some other figures that will pop up are the degenerates. So a straight line, usually you'll have something like x squared equals y squared, and you could just rewrite that as the absolute value of x equals the absolute value of y. And that'll be something like x equals plus minus y. Okay, so that will give you two lines that are in a cross like that. Okay. You could just have a dot at the origin, so that'll be something like x squared plus y squared equals 0. The only point that satisfies that equation will be the origin. Lastly, you could have nothing, right? So nothing, and we saw that happen up here when you have something plus somethings where they're both squared equaling a negative, right? So this would be something like x squared plus y squared equals negative 100 or something like that. It just doesn't work, so you get nothing in the plane. Okay. Okay, so let's go through one example of each. And on the test, I would expect you to kind of do it like I'm doing it. So you're looking in the xy plane, the xz plane, and the yz plane, identifying the traces, drawing little pictures, and then making a conclusion. Okay, I should see all that work. Okay, so those are the possible traces. Now we are identifying traces. Okay, so what you do is let one variable equal 0, identify the thing, and then go from there. And sometimes you can cheat a little bit. For example, the hyperbola of two sheets. If you identify that there's nothing in the middle there, you know it is that figure. Okay, there's no way around it. There's only one figure that doesn't have anything in the middle, and that's the hyperbola of two sheets. So I understand if you use common sense to get your answer, you don't have to go through the motions on me, okay? But at least make it clear to me that that's what you did. So maybe make a comment. It's clear from this observation that I'm dealing with a hyperboloid of two sheets. So from right here, I would say it's clear now that I have a hyperboloid of two sheets. And I'm not going to make you memorize the names of these objects. So what I'll end up doing is kind of, on the test, I'll give you like all the names of the objects, and you just have to figure out which one it is. Okay, so you don't have to memorize the names. Okay, so anyways, let's take a look here at some examples. The ones in the homework are pretty easy because I think they just give you kind of, I think they kind of give you the pictures. You don't even really have to draw this stuff. Yeah. Okay, so it's, yeah. Okay, so anyways, let's try one of these. So, I mean, we could try this guy from the homework. X squared plus y squared over 4 plus z squared equals 1. So the xy plane, letting z be 0, you get x squared plus y squared over 4 equals 1. So definitely an ellipse of some sort. I'm not even going to bother trying to get the orientation. There it is. Okay. Xz plane, then you let y equal 0, so you get x squared plus z squared is 1. That's a circle. Okay. So there. And then my last, what is the last one? Yz. You get y squared over 4 plus z squared equals 1. So again, that's an ellipse of some sort. There's only one object that has 3 ellipses on it. And I mean, if you were to kind of be artistic enough to put this together, you would see, all right, there's a circle here, there's a circle here, and then there's a circle here, right? And if you put all that together, hopefully it's clear that what you have is kind of a sphere, sort of. But they're going to call it an ellipsoid because it's not exactly a sphere, because some of these are ellipses. So, and there's only one choice. Look, it's the ellipsoid. It's that egg thing, you know. There it is. So it's an ellipsoid, and that would be all you would need on my test. So you just do the 3 cross sections that show their ellipses, do little pictures. You don't have to be perfect, and then mention it's an ellipsoid. You don't even have to do the 3D picture. Okay. Again, you could do it in Calc Plot and see, or Calc 3D Plot, or whatever it is. So X, of course, on a test you can't use this. Plus y squared over 4 plus z squared equals 1. Oh, frick. Right, and this is really small, but yeah, I'd have to adjust my axes in order to get it nice. Can I redo my axes, or you're going to let me redo them? No. All right, well, there it is. I can zoom in. So the XZ plane, you see it's a circle. The XY plane, you see it's an ellipse. And the YZ plane, you see it's an ellipse. Okay, so you can go through and kind of check on the, what the heck? Somehow I ended up back in my last section. Did I not make a new? What the heck is this? There we are. All right, sorry about that. Okay, let's move on to another. So I just want to go through all 6 quadrics and show you what they kind of look like when you do the cross-sectional analysis. So let's try this example. We got 16 x squared minus y squared plus 16 z squared equals 4. The xy plane, so you get 16x squared minus y squared is 4. So that's going to be a hyperbola with branches on the x-axis. YZ plane, so we got negative y squared plus 16z squared is 4. So that's 16z squared minus y squared is 4. So the branches will be on the z-axis here. So what is that? Y, z, branches there and there. And then finally on your, what's the last one? XZ. We should have an ellipse, right? So 16x squared minus y squared, plus 16z squared. 16z squared equals 4. I don't have a circle. It's a perfect circle. Okay. So the resulting picture this time, let's see if I can kind of draw it. It's going to have in the XZ plane, so you have the circle here, and then here is the Y plane, and then so in the it's going to kind of go out. So there's like a hyperbola, and then it's going to, the circles will kind of go off on this thing, and it'll be one of these figures, the hyperboloid of one sheet, basically. Hyperboloid of one sheet as opposed to 2 sheets. Let's take a look at it in calcplot. See the truthiness of that. So we have 16x squared minus y squared plus 16z squared equals 4. Check, uncheck. There's a 2 pluses in there. Check, uncheck. There it is. So in the YZ plane, you're seeing hyperbolas on the edges here. YZ. So I guess I got it kind of sideways. Having trouble moving this thing around. So there's the YZ. So the picture in the YZ plane, you know, the parabolas are more flattened like this. Okay? And then in the XY plane, so I'm going to put the Y guy on top. The XY plane, the hyperbolas are more flattened. Okay? That's why it doesn't seem quite right, but those are the hyperbolas like that. And then, of course, in the XZ plane, you just get a circle looking head on there. Okay, so that's hyperboloid of one sheet. Let's move on to another one. So we already did a hyperboloid of 2 sheets. Let's do an elliptic cone. So we have x squared equals 2y squared plus 2z squared. Again, get the xy plane, so let z be 0, so you get x squared equals 2y squared. This is one of those 2 lines. So if you take the square root property on both sides, you get absolute value x equals 2 absolute value y. And then if you drop the absolute values, you get x equals plus or minus 2y, which are just 2 equations of lines, right? X equals negative y, or if you'd rather, y equals plus or minus x over 2. So negative x over 2, so slope negative 1/2 going through the origin. And then the other one, x over 2, slope up 1 over 2 going through the origin like that. Let's look at the YZ plane. So letting x be 0, you get 0 equals 2y squared plus 2z squared. In that case, you are looking at just a point. Okay? And usually when I get a degenerate, what I like to do is push out a little bit. So look at like what happens when I do x equals -1. So if you put -1 in for x, you get a circle. And so it would look like this. And then if you pushed out in the other direction, so you look at x equals 1, you would also get a circle. Okay. Let's look at the last plane, the xz plane. So you get x equals 2z squared. Again, it's just 2 lines like this. And the end object then, if you were ambitious enough to try to draw in 3 dimensions, x, y, and z. So in the YZ plane, as you move out, you're getting these circles. Okay, but as you move in, you're kind of getting just a point, right? And then you can kind of connect these 2 circles as best as I can. And what you end up with is this isn't working very well. Kind of like that, I guess. The heck is that? It's the elliptic cone. Okay, so this would be the elliptic cone. Let's graph it and see what it looks like. And you'll see definitely the x's on the sides and the circle in the middle. Should get rid of that and put in x squared equals 2y squared plus 2z squared. Boom, boom. And there you see it. So on the sides, you definitely see, like in the here in the XZ plane, you see this big X, okay, along the sides. And then in the YZ plane, you're going to see a circle, and of course in the middle there's just a dot, but as you push out you get a circle in either direction with the cross sections. And then finally in the XZ plane, if I can figure that out, there we go, you see a cross again, okay, so an X on the sides. Okay, so that's the elliptic cone. Let's look at the elliptic paraboloid. So the elliptic paraboloid is only going to have kind of a cone on one side. Okay, so example, z equals x squared plus 4y squared. Okay, you're going to see two parabolas. So in the z plane, you'll have z equals x squared. So here's x, here's z, and you have a parabola. In the xy plane, it doesn't seem, you just have a point, right? So you have 0 is x squared plus 4y squared, which is just a point. The only solution is 0, 0. And then in the yz plane, you'll have another parabola, z equals 4y squared. So you get this other parabola, y, and here's z. And then again, if you were so ambitious to graph this thing in 3 dimensions, let's see if I can do it. So you have a point in the x, this is x, this is y, this is z, and the xz plane you have kind of a parabola going like this. In the yz plane you'll have another parabola going like this. And if you were to push out, you would see ellipses. If you let like z equal 1 here, you would get 1 equals x squared plus 4y squared. So as you push out in the z direction, you're getting ellipses. If you tried to go downward in the z direction, you'd get like negative 1 equals x squared plus 4y squared. And of course, in that case, there's nothing there, right? So this turns out to be your elliptic paraboloid. And if you want to, you can graph it, but this one it turns out to be pretty easy. The last kind is the hyperbolic paraboloid. Usually what you'll see are two parabolas kind of going in different directions, and it'll force that shape. Okay, and it looks like a saddle, like a horse saddle. Okay, so anyways, here's one, 3z equals negative y squared plus x squared. And again, let's see the xy plane. So we have 0 equals negative y squared plus x squared. So x squared is y squared. That's just 2 lines. Okay, let's try the xz plane. So you get 3z equals x squared. So that's a parabola. So let's put in our axes here. xz, so it's in this direction, and then yz should give us one going in a different direction, right? So 3z equals negative y squared. So that's negative is going to flip it around the y-axis there, downwards. Okay, and I'll try my best to draw it. I don't think I really can, but okay. So we have our x, our y, and our z. In the xz plane, you have this shape, and then in the yz plane, you have kind of this shape. And if you were to kind of put more parabolas on this thing and then connect the parabolas, you would kind of get what we're after. I don't know, I'm doing my best. All right, so let's go to the cog plot and take a look at the thing. I tried. So 3z equals negative y squared plus x squared. And you see there it is. Okay, so yeah, you get the downward parabola. What the heck? Oh, it's upside down. I got the negatives on the. And of course, it looks like a Pringle chip. There's like a joke online where I don't know if I want to. Yeah, so there's the Pringle chip. They also. Pringles are an example of hyperbolic paraboloids. So hardy, har, har, har. Anyways, there's the upward facing parabola for the XZ plane. There's the downward facing parabola for the YZ plane. And then the XY, you can see the X's kind of in there, at least in the middle. And then as you go out, you'd probably get parabolas. Or hyperbolas, actually. So anyways, there's that, and it's all about just noting the cross sections and then making your conclusion. So in this case, it's hyperbolic paraboloid. So on the test, I would expect 1 point each for each cross section, and then your conclusion, maybe 1 or 2 points for your conclusion. Okay, and so you should be able to go through and kind of just feel your way through these. Obviously, if it's 3 circles, it's not going to be a hyperbolic paraboloid. It's obviously an ellipsoid and that sort of thing. Okay, I think that'll do it for this section. Let me breeze through the homework real quick and make sure there's nothing crazy going on. May have to graph this one using a computer algebra system. You could do cross sections here as well, though, and kind of figure out which one it is. But yeah. Okay, I think that'll do us. So, as usual, thank you for watching, and I will see you next time.